The recorder now, and let's go ahead and get it over with. This is the rock salt on wood session.
A little lemon juice too.
Huh?
A little lemon juice too.
A little lemon juice.
Easy sex with accountants.
And sand.
Yes.
Yeah, don't forget the crucial component.
Yes. I'm gonna figure it out. Come on.
Okay, so this is important, okay? And if the whole class doesn't take enough time to do it, and the highest score is only, let's say, 70%, I would basically scale everything up to like 65% would be 100%, because I'm assuming the person who gets 70% is already A plus. Okay, so I've got to adjust it accordingly. So don't worry too much. If you look at your ranking in the grade sheet and you are saying, okay, the class is about 35 students. So let's say your rank, I don't know. This is just an example. Okay?
45.
So let's say your rank, 34 out of 35. Yeah, then
45.
you have reasons to kind of think about, okay, am I going to be in big trouble here? Okay. On the other hand, if let's say you're kind of in the middle, like maybe 17 out of 35. You will still be about 17 out of 35, which is about a B or a C, in this class. So it's not going to be an absolute, score determining your actual grade for this exam. Yep. The high score of the first exam, I think multiple people got 100%. I cannot be sure. I have to check. But you can check your own ranking though. So when you look at your own ranking, you can kind of tell if you're rank 1 and you're not getting 100%, then obviously nobody got 100%. Is that making sense? Okay. All right. So I'm going to start with this particular exam. I'm relying on Google Documents, getting its Security Act together so that no one can prematurely go into Google Documents and have to look at the exam questions. From the response today, I'm guessing that it's working. Nobody actually was able to preview the questions.
Got job from Google administration.
Well, I would say unless you want to get free housing and free food, don't do that sort of thing.
Try to get job from Google IT.
Not that kind of free, right?
You're breaking rocks or something.
All right, so the first question is JNG to L1. The format of this question is almost the same as the practice question, except it's different, okay? So instead of using a single JNG to L1 instruction, I want you to give me a bunch of instructions making use of JNS, JNO, JNE, and the jump instruction to accomplish the same thing. So what you want to do is to say, okay, here's L1, but what is the combination of flags, or what is the equation that expresses the combination of flags that you want, what is the pattern that you want at L1? That is the question, okay? That's the first thing you have to answer. So what you want to do is, I would just kind of comment here and say, by the time we get to this label, I need this particular equation to be true, okay? This particular formula has to be true. JNG means jump if not greater than, okay? But that's in a signed interpretation, which means if it's not greater than, it means it can be less than, or it can be equal to, okay? But equal to is the same as a Z flag. So I want the Z flag to be a 1, or I want the L flag to be a 1. But there's no such thing as an actual L flag, okay? The L flag is really just the exclusive OR of the sign and the overflow flag, okay? So that means instead of saying the L flag being a 1, I want the exclusive OR of the sign flag and the overflow flag to be a 1. Now, when the exclusive OR is a 1, it means those two flags are different. Okay, one of them, exactly one of the sign or the overflow flag is a 1. That's the definition of exclusive OR. Did you guys remember that part? Okay, all right. So if I spell this out, okay, if I spell this part out, that means by the time I get here, these are the possible combinations. Z being 1 is good, okay? If Z is 1, I should be here because it means equal to. I don't even need to look at anything else. The other part is going to represent the exclusive OR. So I want, this is one combination. I want the sign flag to be a 0 and the overflow flag to be a 1. That's one way to have the L flag being a 1. Because 0 exclusive or 1 is a 1. Is that okay? And then the other pattern that I can also look for is this one here, which is the sign flag is a 1, but the overflow flag is a 0. I know it's hard to read because the overflow, the O, looks like a 0, but that's the overflow flag being a 0. So are we doing okay so far with this little equation here? Okay. I think in my notes somewhere there's an equation kind of like that too, except it's expressed as logical operations instead of spelling out the words. Okay. So that part is actually in the notes. So the question now is, how do I get here using the instructions that we are allowed to use? Okay. So I'm going back here now and say, okay, I know, these are the reasons to go to L1. For any other thing, I would just continue execution. That's what we need. So what I need is I need a continuation label here. Okay, I'll use it later on. All right, we have JNS, JNO, JNE instructions. So the first one might be a JNE instruction. Okay, just to get the 0 flag out of the way. Now JNE is not what you want. You don't want a JNE or JNC to L1 because you want a JC to L1. But wait, we have an unconditional branch instruction. So combining those two, I can actually get this to work. So what I can do is I can say JNZ or JNE, either one is fine, to, I don't know it, I'll just call this, label 2, okay? And I'll define label 2 here. What does it mean if I continue execution after the JNE instruction? When the Z flag is a 1, and when the Z flag is a 1, hey, I can go to L1. Because that means it is not greater than. It is equal to, is not greater than. So this will be unconditional branch to L1. Are we doing okay so far? Now if I get here, that means the 0 flag is known to be a 0. So now I really have to take a look at the overflow and the sign flag. Is that making any sense? Now which one I look at first really does not matter. Okay, I can look at the overflow flag first, or I can look at the sign flag first. Well, I'll just go ahead and look at the overflow flag first. Okay, JNO. Now by itself, if I just know at this point the 0 flag is a 0, just knowing that the overflow flag is also a 0 is not enough reason for me to branch to L1 just yet, because I need to confirm what is the status of the other flag. So I will just go to another label. We'll call it L3. Okay, and we'll do something at L3. So at L3, I will put a comment here to say that at this point we know Z is 0. We also know overflow is 0. Okay, just so that by the time I get to L3 to expand it, I know what needs to be done at this point. If I fall through in this case, what does it mean? It means the overflow flag is set. Hey, if the overflow flag is set, we are looking for the sign flag to be not set, to be cleared. So that means JNS is okay to go to L1. We are done. Is that making any sense? Okay, so for each branch, you really have to kind of comment or at least somehow keep track of what does it mean to get here, what does it mean to get here. That will give you the ability to kind of make all the combinations accounted for.
If we don't, the L1 is just under the condition we compare, and then after I just label, we just jump out, and it doesn't matter where to go. I just jump out.
L1 can be anywhere. You cannot make the assumption L1 is under the code that you're dealing with, because it can be before, it can be after. We don't know where L1 is. Okay, so here when I get to this jump instruction, I know that I have to go to the continue label because at that time, we know the combination is not what we want. So the only thing left is to go to L3 here and expand it. At L3, we already know the 0 flag is a 0. We also know the overflow flag is a 0. So the only chance I can use to get to label L1 is for the sign flag to be a 1. Right? Okay? So that means I have a J and S to continue. If the sign flag is also cleared, then I cannot go to L1, which means I have to go to the continuation label. But if I do not make that branch, which means the sign flag is set, then I can do a branch to L1. So that would be the solution, or one of the many solutions. I mean, this is not the only way to do it, just one of the many ways to do it. Sorry?
No, I thought.
This will be an interesting one to grade because what I will have to do if I cannot eyeball. If someone turned in like blank, it would be easy on me because I can just say, okay, 0, no points, right? If someone gives me something that looks like a solution but it's not what I have here and it's not obvious, I will probably just type it in and run it through a script. And my script will basically run through all 8 possible combinations. Because we have 3 binary flags, so there are 8 possible combinations, and make sure that for each combination it works correctly. So that's probably what I would need to do, which is going to be a lot of typing. Because I don't think OCR is going to work on your handwriting.
We can do online, you can copy.
Huh?
We can do online test that you copy and make test. Yeah, just copy our work and copy.
Community service, right? Yeah. Okay, for question number 2. Now, question number 2, instead of asking you for the final bit pattern, I decided to give you all these steps so that every step along the way you can get partial credit. If you run out of time, then I'll use all of these steps and say, oh, okay, this person got halfway done or 75% done, even though the final bit pattern is not done. There'll be partial credit. Yes?
Like if I get final product, but I didn't put there, then
let's see here. Well, but then you won't be filling all these slots.
I didn't fill there, but I get all my.
Okay, well, we'll have to take a look at that.
Sure.
All right, so let's assume that we are using the first case. Okay, so we are dealing with 0.375, which is 3/8, right? 0.375 is 3/8, so 3/8. There's a reason why I picked that particular value instead of like 0.4, which seems to be convenient, right? Yeah, if I pick 0.4, then you guys would be going like. Okay, so 3/8 is good, okay? Because I want you to express that value, which is in base 10 right now, as a sum of unique powers of 2. Okay.
That's a 0, 1, 1, 0.
Well, not yet, not yet. This is I'm trying to get it so that it's easy steps for each one so that you guys can just kind of follow the steps and get, so this would be, you can write it in different ways. You can say this is 0.25 plus 0.125, or you can say this is 2 to the power of, okay, 2 to the power of -2 plus 2 to the power of -3, okay? Or you can write 1/4 plus 1/8. There's a variety of ways you can express this, and I will still count that as a correct answer. Is that okay so far? Okay. How many people did this part okay? Just expressing it as a sum of some kind of negative powers of 2. Okay. So the next step is to take something from this step and say, now I want to express it as a binary number. Using a binary point, I cannot call it a decimal point, a binary point, and say, okay, how do you express it as a binary point number? So in this particular case, it would be a point. I don't have a 0.1 here because a 0.1 is a half. So there are 0 halves, 1/4, and also 1/8. So in this case, it's a 0.011.
I got that part. I got that part, but I put underneath not there. Like I solve it,
Uh-huh.
Try and implement there.
So you're ignoring these instructions. Express x as a sum of blah, 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 blah.
No, I solved underneath, but don't have time to implement that there.
Okay, so this step is something, some people have a question about this one, about normalizing. Normalizing is to take the 0.011 and turn it into the typical mantissa representation. The mantissa representation means it is something that is non-zero point, blah, 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 blah. But when you turn this number into 1.1, in this case, you have to compensate by an exponent of 2
Negative 2.
to deal with the shifting, right? Okay, so in this particular case, it would become 1.1, in base 2 times 10 times 2 to the power of what?
1023.
Well, it depends on
11.
how many times I have to shift. I shifted
11.
twice, so that means I have to compensate it and say, okay, we have to multiply it by a quarter. Yep.
If we didn't put it that if we didn't indicate it was a base 2 number, we quite thought.
Okay, normalize the number from above, and the number above is a binary number. So if you did not explicitly say this is a binary number, I will interpret it as a binary number, unless that number somehow involves digits like 4 or 5 or whatever. that is obviously not a binary number. Okay, is that fair?
Yeah.
Okay. All right, but you still have to give me the exponent of 2. That one can be in base 10. Okay, so in this case, negative 2 is in base 10. Okay. All right, so moving on to the next step here. What is the fraction of the mantissa as a 52-bit binary number? But I don't want you to give me a super long string of zeros and ones because I'm not going to count. I want you to give me 13 hexadecimal digits because one hexadecimal digit is representing 4 bits. 4.
Yes. Byte goes to
So 52 divided by 4 is 13. So I need 13 hexadecimal digits. So in this case, we are looking at the 1 here, okay? But the 1 but I only want the fraction part. Now the fraction part means only this part here, only the portion to the right-hand side of the binary point, which in this case is really just a 1. So that means the binary bit pattern that needs to be represented to answer this question would be 1 followed by 51 zeros. Okay? Which is a fairly easy number to convert because only the first or the most significant hexadecimal digit is an 8. Everything else is a 0. So you just have to put down the 8 and then count 12 times. 0, 0, 0, 0, 0, 0. Okay? So in this case, this part is 8 followed by 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. And in hexadecimal. Okay. And since I asked in the question that I want this number to be in hexadecimal, if you forget the 0x, I'll give you a pass. Okay, I'll understand that this is already a hexadecimal number. Okay, are there any questions about this step? Questions? Okay. What is the exponent of 2 after offset in decimal? Because in a double precision floating point number, the exponent portion has an offset. Can someone tell me what is the offset amount?
1023 minus 2.
1023 is the offset. So in this case, because the actual value I want to represent is negative 2, that means I have to add 1023 to negative 2, which will give us 1021. Okay. So we have 1021 here, okay? And since I do not ask you, this is a base 10 number, so without any prefix, it's going to be a base 10 number, and that's what I need. Yep.
Doesn't that question ask what's the offset when you move the decimal point?
It asks you what is the offset, but the offset is the 1023.
So the second one would be the 52? For the question after that, would that be?
The question after that is what is the exponent of 2 after offset, but you're changing the base to base 2. So I first ask you what is it in decimal in base 10, and then I'm asking you how do you represent this as a binary number. So it's a base conversion. Okay, so I want you to calculate it, one step at a time and not roll all the steps into one single.
I assumed I knew what you were asking, so.
Oh, so you anticipated that.
Okay.
Okay. Well, I'm not gonna pick on stuff like that. Okay, so if you get one right, that is obvious that you got the other part right. Okay, that's fine. Okay. All right. So here's the base conversion question, right? Okay, here we have 1021, which is a fairly large number, and how do we convert this into base 2? Okay, quick tricks. Does anyone want to mention any quick tricks to deal with this? What is 1023?
It's 0 1 1 1 1 1 0 1.
How many ones? I know they're all ones. How many?
10.
10 ones. Okay, 10 ones is correct. Okay, so and if you compare 1023 and 1021, how much off is it? 2. So we just take out the 1 representing the 2, and the rest is correct. Yay! So that means this is an 11-bit number. The first bit, the most significant bit, is going to be a 1. Then we write 10 ones here. Then we'll go back and flip the other one. Okay, 1 2 3 4 5. 1 2 3 4 5. Change this 1, which is representing how many 2's we have, into a 0, and we have the binary number. Yep.
So you don't have to move the binary point 52 bits to the left?
That is implicitly done here, but we don't have to adjust the exponent. We do not, because it is implicit. The binary point is implicitly already here.
Yeah.
So we don't need to actually make the adjustment. Now, in the homework assignment, we have to do the adjustment because in that case, there's no implicit point. The actual point is right on the right-hand side, and that's why when we have to actually do the shifting, we have to account for the number of times we have to shift it. But in this case, it is already implicit to have a point over there. Okay, and what is the sign bit?
Positive.
And since all of these numbers are non-negative, the sign bit is a 0. And what is the overall binary representation of x as a double precision floating point number? So what you do is you combine the 0 as the most significant bit. So you basically have 0 0 1 1, which is a 3, and then you have an F here. So 3F, and that will make a D here. So 3F, D, and then 8 followed by all zeros in this case. So that would be 3, F, D, 8, and then all zeros. And since we need 16, well, see, I did all the calculations for you. There are supposed to be like 16 digits. Once you know the most significant 4 are 3, F, D, 0, D8, and the rest are supposed to be 0, you just have to count 12 zeros here. 1, 2, oops, wrong place. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. That would be 12. Yep. So that's the answer for 0.375 as a double precision floating point number. I'm going to have to use my camera to take a picture first.
Yeah,
But did you guys follow the steps? Because if you follow the steps, you will be at least getting partial credit, even if you don't have enough time to finish the whole thing. And since you did not have enough time, you decided to skip all the steps and get to the final answer. All right. Question number 3. Okay, question number 3 is just saying that X is a base 10 number from the rightmost 2 digits of your student ID, so whatever it is. Okay, we'll just make the assumption it's 37. Okay, 37. All right. So given that is the case, so we are going to substitute it with I'll just use 50 because 50 is in the example here. So we have 50, which is 50, which is in base 10. Okay, that's fine. So I want, this question is about specify a range of values for the missing part here, okay, the underscores. And what I want is the result to have the overflow flag cleared, okay? That's what I want. So what you are looking at will be the binary representation of whatever is in AL, which are the underscores, minus the binary representation of 50. This part here is not actually that important. All I really want is to make sure the overflow flag is clear. So I want you to give me a range of value for this part so that the overflow flag is clear. Okay. So how would you go about doing this? Well, let's take a look here. Let's take a look at how we can approach this particular question. So I want some kind of value, which is x here. Okay, should not use x because x is already used. So I'm going to use y. Okay, I want y minus x to be something, and the sign makes sense because the overflow flag being cleared means the result makes sense, and a comparison is the same thing as a subtraction.
Yes.
Did say that.
Did mine say add? Didn't say that mine said add. Oh.
Mine said that.
Now, from the time I gave you the test to the time of display here, I changed the add B to a compare B. No, I'm just kidding. No, it has been compared by the whole time. Oh, man, you did not read the question carefully.
Okay.
Okay, so compare is subtract, okay? And we are subtracting the first operand from the second operand. That's how subtraction works.
It's in the other flags that matter though. So I assume it starts with 0.
Okay. All right. So getting back to this question, if you're dealing with subtraction and you're subtracting a non-negative number, under what circumstances will the sign make sense?
Positive.
You subtract a positive number from positive number, then the sign can be whatever. It still makes sense. Okay. So that means we know at this point that y is going to be a non-negative number. Okay. But it can be any non-negative number, because if you're subtracting a positive number from another number, the other number only has to be non-negative. It can be any non-negative number. The sign will still make sense. So that means, in this case, y is going to be an element of 0 all the way up to what is the most positive value that you can represent using a bits.
255.
127 in signed interpretation.
Yeah, but you put negative numbers in.
But wait, that's not the entire answer either, because for certain negative numbers, the overflow flag is also going to be clear. Think about it. -1. You subtract 50 from -1. The answer is, hey, that's just -51, right? Can -51 be represented using a-bits as a signed number? Yeah. Yeah, because we can represent all the way down to what? Negative
126.
128. Okay? -129 is the first one that we cannot represent using only a-bits, using signed interpretation. So the second half of this question is y also has to be in -1 all the way down to a particular number where you subtract 50 from that number, you end up with 128. So that would be 128 minus 50, which is 78.
Yeah.
So down to -78 will still be okay. Yep, go ahead.
Does it say it needs to be signed?
Yeah, but if you use unsigned numbers,
Sign, yeah.
Because I don't
You
see.
can use the unsigned representation.
Oh, okay.
So that means -1, you can use the bit pattern of FF, 0xFF, all ones, 255. All of those things are meaning the same thing to me. but you still have to give me the right range.
So
Okay.
when you say 0 to 65.
As I said on the first page of the instruction, I don't really care about what base you use, as long as it is still representing the same bit pattern. Hey, you know what? I'm good. If the assembler says it's good enough for me. So that means the negative one, you can use 0xFF to represent it. Negative 78 is, let's figure out what is that negative 78. Okay. Negative 78 as a value is the 2's complement of 78. Is that okay? That's how we take the negation. So that would be 64 plus 8 plus 4 and then plus 2. I think that's 78, right? Okay, let's double check. My math is really bad. Sorry. Yeah, that's 78. Okay, so that's correct. So that means we have 0, 1, 1, 2, 1, 4, 1, 8, 0, 16, 0, 32, 164, and 0, 128. So we take the 2's complement of this particular new pattern, which means we flip all the 0's to 1's, we flip all the 1's to 0's. So that's 1's complement, and there's one extra step to it. Okay. And then we have to add 1 to this. Okay. So once we add 1 to this, we have the actual final pattern, which is 1, 0, 1, 1, 0, 0, 1, 0 in base 2. That is representing the same thing as negative 78. And this is also known as 2 plus
10.
16.
Are you trying to turn into X?
Yeah, I'm turning to decimal first.
Oh.
So we have 128 plus 32 plus 16 plus 2, which is, man, I cannot do that. That's 160, 176, so that would make it 178. I think. Hmm? Okay, 1, 2, 4, 8, 16, 32, 64, 128. So 128, 32, 16, and 2. These two add to 160. What am I talking about here?
30.
I got this.
Just add 128 to negative 78, right?
Hmm?
Add 128 to negative 78, and you get the sign version. Is that
Yeah.
also another way to do it?
That's the other way to do it,
That's
but
not how you do it.
I'm obsessed with doing it this way. It is 178. So that means you can specify negative 78, you can specify 178, you can specify the bit pattern, which is 10110010. You can specify it as a hexadecimal number, which is a B2, okay? And all of those are acceptable answers of one range of the number. The other side has to be 127, because 127, 0 followed by 7 ones, 7F, choose your base. Yep.
Why is that? 0 only to 127?
Well, you combine these two.
A1 we done that.
Okay, so what you do is you combine all of this stuff here, so it becomes negative 78 to 127. That would be the final answer.
So if I use 128, then what's wrong there?
It's
If you use 128,
Yeah.
128 is the same representation of negative 128. So in your case, the overflow flag will be set.
So
How?
it's a trick
how
question.
AL is
That's the
8.
question.
The AL is 8 bits.
No. The processor never tricks.
Yeah.
Oh, I know. I thought it was unsigned for some reason.
So the AL is 8 bits.
What?
AL is 8 bits.
AL is 8 bit.
If
Yes.
I put it 9 overfly, which means I can put it all 1, 8 1 there. Is that right?
That's 128, right?
yes.
Okay. And what is 50? Well,
It's 32 plus
Did I use spelling?
But this is 8 bits, is that right? But I still can, this is not over, the flag is not over, not on, is that right? Over flag is not on.
What?
This is the flag is not.
This is a, I cannot hear that word.
Is
Flag.
that 128?
Yes.
This is 128, yeah. 1, 2, 4, 8, 16, 32, 64, 128. I know those powers of 2 more than I know the denomination of money. Because I use base 2 numbers more than I use pennies and nickels and stuff. Yep.
So I have like the correct unsigned, or the correct sign range, like off to the side, and then when I converted it to the sign range, I got it wrong.
I will have to take a look.
Okay, so
Yep.
When you use 1 followed by 0, which is 128, but why don't we can't use the 1, 1, 1, 1, 1, 1? Our last one is 0. Why?
All ones?
Yeah, and the last one is 0.
Well, all ones is a part of -1, which is in the range here. That works out.
No, I don't put a 0. And last one is 0. 1, 1, 1, 1, 1, 0.
That is negative. That represents -2.
That would be a different answer.
Okay, let me answer Tristan's question. Okay, Tristan has a question.
It was, I would see it as from 50 to 255 would be valid, because I've noticed that when you do a compare and it with unsigned, and it becomes say -1, it will throw a overflow flag.
Well, there's no, okay, the compare instruction does not care about whether it's signed or not.
Yeah.
Okay, you know, it's the individual flags that pays attention to the sign flag of the 2 numbers that you're subtracting and also the result of the subtraction. This is the right range for 50, for 50. From -78 to 127 is the correct range where the overflow flag should be cleared after the compare.
I think I'm thinking of the carry flag.
It is the same flag, except this is a subtraction operation and not, oh, okay, never mind. Okay, it is not the same flag. The carry flag and the overflow flag are different flags.
I was remembering it as the overflow OF flag being set, but it was the carry flag being set.
Oh. Okay, so for question number 4, I think I might have miscalculated a little bit here, so you guys can probably get this one as a freebie. Some of you, anyway, you know, look at this there. Hey, that's easy. The following code is supposed to find the maximum of EAX and EBX interpreted sign, and then update ECX with the maximum of the 2 numbers. Okay? It does not quite work the way it's supposed to. Okay?
I found one.
So okay, but if you read this part here, then you'll find the whole of the question, because I said, you know, I don't need you to fix the problem. However, find the test case that this program will not fail, will succeed. That's actually very easy to do. Finding the maximum of 2 numbers that are identical is always going to work.
You know, I thought about that when I was like, that was
That would be too easy,
Yeah, I
right?
was like,
Coming
yeah,
from Jack, that's
I
going
was
to
like,
be
that
too
can't
easy.
be.
So you second guess the answer, like,
I was like, you know, I'm like,
no, but that really is. That really is what it is. Okay.
And I changed my answer. I really think so. It's like 55%.
But that's only one test case where it will succeed. If you find any test case that it will succeed, it will still count. Okay. Yep.
Technically, they're the same numbers, except when it to ECX, don't you get the maximum value out of those 2?
Yeah, that's what he said.
Yep. That's exactly what I said.
I did 0.
Yeah, no, but I'm thinking, I'm like, as the programmer wouldn't be confused about that. He would know I put the 2 same numbers in there.
Right, but I didn't say the 2 different numbers. I should have said 2 different numbers.
And
then it would
say
say
he's a good programmer.
Then it would
It's not because he wrote that line, so.
Yeah, well, yeah. So if you give me the same number, you know, for the first case and for the second case, you know, they will work. So give me 0 and 0, 0 and 0, and that's like 6 points right there.
Why did I do that? I only got 30 because I overthought it.
It is 6 points.
No, I'm saying I only got 3 because I missed that.
Yeah.
Wow.
Okay.
I thought it was
So I kind of goofed up on this one. You know, I kind of made it a little bit too easy. On the other hand, if I said, 2 different numbers, that would make it a little bit harder.
Well, that's what I was trying to do, and I made it a whole lot.
Okay.
I just kept going like, well,
Okay. Question number 5 is, I just want to kind of use your student ID as the seed of this particular program. Okay. So what I'll do is I'm just going to keep the MNOP as it is. So this way you can relate the answer to your exact student ID in your answer. Okay. All right. So what we want to do with this one is we want to lay out the memory and basically know how the bytes are arranged. You guys do okay? No?
If we didn't put our student ID, just put the letters.
You can do that. Although, if you did that, you definitely did not. You missed some of the instruction. So
Wait, so you wanted the things that you didn't specify to take the place of the middle numbers?
yes.
I thought, because I kept looking, I'm just like, this is a hex. You know that M are not
I just wanted to make it real difficult for someone to copy the answer from somebody else, or make it so obvious that I can tell. Oh, not only did this person copy the answer from somebody else, I know exactly whose answer is copying from. It's Okay, so if we look at the memory layout of this particular program, we have the first dot int. We don't know exactly what those 4 bytes are because we don't know where L1 is. So those 4 bytes will be some question mark. Okay, but it will take up 4 bytes. The dot int will take up 4 bytes.
So if I read that right, what that statement says is that
You mean the dot int L1?
yeah, the dot int L1 is that we're going to store 4 bytes starting at the location.
How you
or
did
that?
it.
Okay.
Okay, the first byte, the least significant bytes of these 4 bytes is the address L1.
Yeah, so which is the label itself.
Which is the label itself.
Yeah, so just basically the label says I'm pointing here.
Correct. It is pointing to itself, in other words. It is its own address.
I'm here.
Yeah. Okay, so this is L1. And the rest would be pretty easy because the first one is the MNOP0000. So that would be, in this case, 00 first, and then we have OP and then MN. Because it's the little endian representation. Oh, MN. Sorry. There we go. Because we don't switch within the same byte. Yep. Okay, and then the next one is PQRS. So we have RS, PQ, and then 0, 0. Is that okay? And then we have the dot word 0 MNO. So we have NO and then 0M. Okay, I know you guys cannot see it right there. And then the last one is PQR0. So it would be R0 and then PQ. So that's the exact pattern that we should find in memory after the all the dot in and the dot word directives. Is that okay?
Yes.
Okay. But that is not the question, right? This is not considered an answer because that's not what I'm asking. What I am asking is after each operation, what is the value of the registers? That's what I'm asking. So what you need to do is to keep an eye on the memory layout and answer the rest of the questions. And excuse my cursor moving here because I can move the cursor by the keyboard without overlapping the windows. So I can still look at the memory layout. There we go. All right. So what is the first operand of this move L instruction where the OP cursor is? It's not an immediate operand, it is a direct operand. But whether it's immediate or not, that's the same thing. So you still end up with what in EAX, the address. The address, exactly. So we end up with L1 in EAX.
If we had put ampersand.
Ampersand?
And
I guess it's okay, because
Right.
in the debugger, you have to use ampersand to extract the address. But it's the same thing.
Yeah, just
the
that.
address of L1 is L1. Okay?
So all labels are just, if we want to put it as C, their addresses, they're just pointers. All labels inside of assembly will be just an address and stuff.
A label is a constant. It's kind of like it's not even represented once the program is assembled. So a label is a construct that is used by the assembler to represent a particular quantity as a symbolic name. Okay? But in this particular case, because we have L1 after the dot int, it is actually consuming memory when your program runs. But normally, with like the jump instruction one, that label does not use up any actual space in the actual program, because all it is to say, hey, this location in memory is also known as L1. So later on, when you have a JMP L1 or JNO to L1, the assembler knows where you're talking about. Okay. All right. So we are adding 3 to EAX, so that means EAX is going to be L1 plus 3. Okay.
And that 3 means they pointed always
Huh?
value 3.
It's L1 plus 3.
Just like if we put a present, which means a value.
If
that
you
was
add a ampersand L1 plus 3, it would still be the same thing. Okay, so now, but this is where it makes a difference. Okay, so this is L1 plus 0, L1 plus 1, L1 plus 2. This is L1 plus 3. Okay, so we want to put L1 plus 3 indirect into EBX. So that would be these bytes. Okay, but you cannot say question mark 0000 OP, because it is using the Little-endian representation in memory. When you specify the content in a register, you have to use the most significant digit on the left-hand side. So the way you look at the content in EBX is going to be 0x OP0000 question mark. Those two question marks will eventually go away. Okay, they're only here in the interim, but they will go away. Okay. Next instruction. What is L1 plus 9? What type of operand are we talking about here? It's a direct operand, which means we are going to the location, L1 plus 9, grab 2 bytes starting at that location, and put it into EX. And we'll be using the Little-endian standard as well. So you just have to count. This is plus 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. This is 9 plus 9. This is plus 10. So these 2 bytes will be copied.
Is that,
Oh, did I count wrong? Okay. This is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, there we go. I missed it. Double counted somewhere. Okay. So it would be 00 PQ put into the least significant 16-bit of EBX. But since the question is asking you what is EBX, you will have to keep the other portion and only overwrite the least significant 16-bit by 00 PQ.
is that L1 plus 9, which means starting from the end of L1 and then go next 9 bits.
Say again?
L1 plus 9.
L1 plus 9 means 9 bytes after the byte at L1.
Yeah, so which means we start L1 is the 4 question mark, 4 bits question mark, and then we can cross 9 after, is that right?
This is plus, okay, look at the screen. This is plus 0.
L1.
And if you count this, it would be plus 9.
From beginning.
Yes. Okay, so now we have EAX again, okay? But what exactly is EAX in this case? Okay, first of all, what is what?
Address.
Well, the value of the label underscore start minus 4. So what you can do is, well, we can express this as L1 plus some constant if you want to, or you can just keep underscore start minus 4. because it's a move immediate operand, right? With a move immediate operand, whatever is after the dollar sign is going to be copied to the destination register. So in this case, it really is that simple. It's just that. But for those of you who really want to make this more complicated than it has to be, then you can say, underscore start is actually here. This is underscore start, right? So you can say underscore start -4. This is -1, 2, 3, 4. This is -4. So -4 is also known as +9, +10, +11, +12. So you can also say L1 +12 if you want to. I doubt anyone is actually doing that, but yeah. All right, so now we are going to overwrite BH with whatever EAX points to. So that's just going to be overwritten by NO, right? So now EBX becomes 0x OP 0000 NO.
Maybe, right.
So this is sorry?
BH, not BL.
Oh, BH. That's right. Okay, sorry. EQ. These two. Okay, never mind. Okay. There we go. Very good. Good catch. So that's the final answer, and this one is set up so that you can get partial credit as well. Okay, so if you follow along, okay, this register is getting this value, this register is getting this value. Even if you cannot finish the whole thing, you get some. You can probably get some partial credit. Unless someone on the very first line says, I have no idea. Then the rest will be kind of like, how are we gonna?
Gotta at least fake it.
All right. Question number 6 is writing some assembly code to do this. Okay. This is actually a somewhat well-known algorithm to draw, to do divisions by addition and comparison only. So it's a little neat trick, okay? All right, so how would you write this code? Now, I did not ask you guys to show me all the steps, so there's no need to show me the flattened version of this particular assembly code. You can start translating right away. Okay, and your structure, the structure of your code does not have to 100% reflect the C code. So if you can see, oh, there's a shortcut to do this, hey, go ahead, go for it. Okay, as long as it is functionally the same, it will still be okay.
So you can be grading on the script. You're going to be grading the script.
Grading with a script? No, but I can usually eyeball and see if all the key components are there. So I will talk about the key components right now. Okay, EDX gets 0. I think that's a pretty simple one. So I may not even assign any point values to this one.
Solid 10 points.
I was positive about that one.
I will take points away if it is done wrong.
I was looking at this and I see, in C, EDX would be a variable. So assigning 0 to it is like clearing out all the values.
Right.
If you're just moving along to ECX, that's not necessarily zeroing out all values.
If it's 32 bit,
Okay, right. What if we made it 0 a different way? If it still has the value 0, 32
just have to make sure it has a value.
Okay.
So you want us to assign 0, not that?
Well, there are different ways to zero out the register. You can say, subtract long, EDX, that will turn it into 0.
When you start the program, they're already 0.
Well, you can do that.
No, you cannot make that assumption because this chunk of code can appear anywhere.
Yeah. Wait, so you can subtract.
Well, I didn't assume that. I'm just asking.
Both the operands can be the same register?
Yeah, they can. Yeah, so if you do a subtract long %EBX, comma %EBX, it will do the same thing as moving a 0 into EBX. Okay, so now we have a while loop. So the general approach with a while loop is you change the condition to be exactly the opposite. In this case, if EDX is greater than or equal to 10, you get out of the loop. Okay, that's the usual way to do it. So what you do is you compare long 10 to percent EDX, and you say, okay,
Above or greater?
okay, so you want to look for the opposite of less than, which is not less than, right? Less than versus not less than. And this is all unsigned, so if it is not less than, we don't call it less than. What do we say?
Greater.
Not below. Okay? Well, not below is the same thing as no carry.
Wait, so
okay, so you can pick one of those.
Now you answer the question.
Okay.
Is it B? Is it JB?
J and
B.
B.
Can we use
No, I
Jump
wanted
above.
to jump before below. I got it.
Okay, so in this case, J and B will do it. J and B, J and C are exactly the same thing. Okay? Pick one. And we'll say jump to while exit. I will not grade based on the label name. So if you don't name it wild exit or wild end, I'm not going to take any points off. Yep.
Can we use
Would
J
jump
and
above
L?
and then a jump 0 after that, would that be the same as jump if not above or below? Crap.
Yeah.
How did you do it?
Jump not
Instead of
above.
jump not below, I put jump above and jump 0.
Okay. Not below is
Above
above
and
or 0. So you have a JA followed by a JZ, or something equivalent to that. Yep. That's a scenic route to do it, but yes, it does get you
I didn't know
there.
about J and B because I missed that lecture, and it was 7 seconds long on YouTube. So.
Okay,
Yeah.
well,
Yeah.
the scenic route works.
Yeah.
Okay, you still end up in Monterey, so it'll be okay. Yep.
Since we only increase 1 to 20 every time each one, which means they will follow to 10, which means if I use as long as not equal to 10, it should be fine, is that right?
Nope.
Jump out.
Is that what? If it's not like a 10?
She's saying JE instead,
Yeah.
Yeah.
but that would not be the same as this code here.
Yeah.
You get some points off.
I said I use J and L.
Hmm?
I said I write J and L.
J and L?
Yeah, not less than.
Well, then why would I write down here they're all unsigned? You have to use the unsigned version of the branches. Otherwise, there's no need for me to write down whether it's signed or not. I mean, if I say explicitly it is unsigned, then you have to use unsigned.
I said it's positive.
Hmm?
Yes, positive.
Yeah. So. J and L.
But you are only relying on the fact that this is this is 10 and not something where the sign bit is going to matter. That's not, you have to translate it the way it is, okay? The meaning is it is unsigned and you have to use the correct instruction to do it. Because otherwise you can say, hey, since EDX can only go from 0 to 10, why don't I just use DL as a byte operation? It will still work.
Yeah.
Can't do that. There's no shortcut in life, nor in programming.
Sure there is.
Yeah, but it will come back and haunt you like there's no tomorrow, because there is no tomorrow if you take a shortcut. You will wish there's no tomorrow if you take a shortcut.
I'm thinking go to. So yeah, go to. Those are shortcuts.
The G word? All right, so we are in the loop right now. Okay, so the first thing I would do in the loop is to have a branch to go back to the beginning. Okay, because before I forget, I'm gonna say, hey, we need to go back to the beginning, which is while begin. And the while begin is right here, before the compare. Okay? Now I know I can do this because I have an editor. In case you have all the kinds of insertion and editing marks, that's okay. As long as I can follow it, you can still say, oh, okay, I meant to have this instruction between these two lines. Okay, that's actually okay. All right, so what do we do in the loop? Well, we have this condition here that has a plus equal operator. And once again, I'm assuming that you guys remember from your C class what is a plus equal. What does it do?
Add.
It's called a compound assignment operator, which means it will perform the operation and then update the left-hand side with the result of the operation. So did you get it?
Yeah, I got it.
So all I could tell
I
you
knew what it
doing
was.
this test.
I knew what it was. I just didn't know if,
How to
if
do
it
it.
actually updated EAX.
Okay. If I were to specify just plus, it would actually be harder.
Yeah. Oh, like you
Yeah, but then I'm like,
I thought this was
You're
funny.
saying in C, it's the left-hand side, not in assembly.
Well, yeah, just
Correct.
saying
In
it's-
assembly, it's the
Freaked me
opposite.
out there for a second.
Yeah.
Yeah, so in assembly
No,
it's
but
saved
yeah,
on a
Right.
left
The
side.
destination is the second operand in assembly, which is what I'm going to do here. Add long
Not the left.
EBX to EAX.
No, yeah, he just means the left.
Okay?
In C.
So add long EBX to EAX will accomplish the compound assignment operation because it will do the addition and change the
The register of the destination.
the destination. Yes, that's a better way to put it. Instead of right-hand side, left-hand side, or the first or the second. Yeah, the destination will get updated correctly. Then we can do the compare, right? So in this case, I'm looking for the condition of greater than or equal to get into the then branch. The typical way to convert a conditional statement is look for the reverse of this, okay, the negated version of this, which is looking for the less than, okay?
Really?
Well, I mean, that's one way to do it. So I'll be doing compare long, and I will specify compare ECX to, what should I compare to?
EBX.
Yeah.
EAX. Because the addition, the result of the addition is stored in EAX. So
Yeah.
EAX is what I need to compare to.
Plus, from C, you just know that whole parentheses has the same value as the
Right, and then jump below to get out of the conditional statement, which is and if, and I'm going to define and if right here. Okay. If I do not go to the end if, it is time to actually perform the operation, which is another compound assignment operation. We want to subtract ECX from EAX here. Yep. Go ahead.
Oh, but it also works if it's equal.
Say again?
Yeah, the condition also goes through if it's equal.
Yeah, so no, he's doing the opposite.
I'm doing it. I'm branching away if it is the opposite.
Oh, does that include equal?
Yeah.
Oh.
No. Below does not include equal, which means if
Below
it
is
is
less than.
equal, I'm going to go for the then branch.
Yeah.
Okay.
He's just choosing to kick out.
Yeah, below is the
Yeah,
same thing as less than,
yeah, I
but
got
for
it.
signed for unsigned comparison. Okay. And then I have to add one to EDX. How do we add one to EDX?
Increment.
Add long one to EDX. Wrong.
Whoa.
Dollar sign. If you miss the dollar sign, I'll take points off.
Can we use the increase?
Huh?
Increment.
Increase.
Increase?
Yeah.
But we never talked about the increment operator.
We, it works on the computer.
Huh?
It works in my program.
How did you learn the instruction?
We can study more.
Hmm? Sorry?
We use.
I don't think we ever talked about the increment instruction.
But you,
Yes,
you, did give us,
yes.
you gave us a user manual.
Yeah, you gave us
Yeah.
documentation that lists it.
Oh, okay.
Yeah.
Well, that's fine. Go ahead and use it. That's fine. You know, if you find it, you can use it.
Because we used in our last.
And I think that's it. That's the entire code.
Assignments.
Hmm?
We used that in our last two assignments.
Okay.
He doesn't say you can't use like
But for that instruction that I confine you guys to use JNO, JNS, jump, and JNE or JNZ, you know, that one you cannot use anything other than those.
No, when I was working mine, I had it with the carry, and then up until I started writing, I realized, oh wait, he doesn't have to. And I don't think it would have worked now, but okay.
Okay. Oh, no, you good? Okay. Yep, I think that should do it. You know, that's actually,
That's basically it.
all right. So are there any questions about this test?
So that was just
Which question was the hardest? which question was like,
Exam
yeah.
number 2.
Which one?
Exam number 2.
The breaking down,
The floating point one?
the floating point one?
That one is the easiest one.
Like, the way you do it isn't exactly like the way that I've been doing it, so.
Yeah.
I just got through a couple of them and it would have taken me too long, so I just moved on, and then I never was able to get back to it in time. So it's just all that.
On that note, like Wikipedia's got a really good graph to explain how to do it, which it's different from the way it is in those steps. It breaks it down in a different way.
Okay.
So I got an answer which I think was wrong. Steps were skipped.
I felt the same, but it was just more of I had already struggled with my own problems. So like, once I seen that, I was like, I don't want to feel about this. I just
And then the one where
But
you said
that's
you made the
much
mistake where it could be that they're both equal.
Yeah.
Yeah. And I went and asked you, man, I came down here and I was just like, I wasted like half the time just going over that problem over and over and over again. I didn't realize I already had it right.
Yeah.
I found the other way you wanted to do it eventually.
Oh, okay.
But I wasted so much time.
I had to convince myself. I'm like, there's no way he's going to clear up. No, I'm like, there's no
So
way.
other than
One
that,
and one,
you know,
two and two.
No, then I think, but I guess it's mine. I was really tripped up, not tripped up, just really confused on what the L1. I was pausing, I was like, this has to be.
The L1 colon.
Yeah,
L1
just like,
colon.
since I hadn't seen it, I was just like,
L1.
what is that? I'm like, what does that mean? Like,
Okay, I think you can do it in C even. Okay, so this is.
oh no, you did a good job of explaining it now, 9.
Because that one is kind of the same as doing this.
Yeah, that one counts. That was the hardest one. L1.
Oh yeah, cause no, cause I just.
I didn't even, I was like, what am I supposed to do with this?
Like, what does that even mean? I'm like,
Like add 3 to L1?
I think you can do that in C.
wait, me is
a void pointer, but I want a pointer. I want my own address.
Oh no,
to be
okay,
stored
that's
in
just
my
my, okay.
So it's basically the same thing.
So you can do
L1 colon dot in L1 is basically doing the same thing. You're allocating the space of 4 bytes, which is the size of what you need to store an address. But whose address are you storing? Your own.
I gotta see about that. I gotta see about that. Not that I don't believe you, Cal.
I don't believe myself either. So let's do it. Let's do it. And we'll throw in pedantic too, just in case it is a weird thing that GCC decides to accept, but it's not in the standard. Okay. You know how those things go.
Well, it didn't say anything, but maybe
it didn't say good job, Tack. You know,
it didn't say it was correct.
it may be questionable.
It's like, I'll get back to you later.
Alrighty. Any other questions?
Beautiful day.
Beautiful day.
Are we going to go on our assignment?
Alrighty. Question?
Are we going on our assignment?
I guess we won't have enough time to go over the homework assignment. So this part is probably useful. Alrighty.
Can I